as mentioned in the previous lesson, in this lesson we are going to start to look at some what we call valid forms of inference, ways in which we can infer validity, some kind of inference rules for creating valid arguments that apply to any argument whatsoever. Okay, so we've already looked at what a valid and a sound argument is. We're going to put aside sound arguments for the time being and come back to them when we look at informal fallacies. And in the next few lessons, we're just going to focus on valid arguments and specifically valid inference rules. So the inference rules we're going to focus on include the modus ponens inference rule. These are all Latin, by the way. The modus tollens inference rule, and also the rule of inference by reductio ad absurdum. So, as we've already talked about in previous lessons, a valid argument is one where if the premises are true, then the conclusion has to be true. The premises lead to the conclusion. We can use what we call inference to analyze any given argument, regardless of the length of an argument. So this is really a way to look at how we structure an argument. So if you get a bit bogged down with the idea of what we call inference rules, instead think about them as more like ways in which you can structure an argument, like given rules to how we structure an argument, such that if you structure if no matter what the argument is about is structured in a certain way, it will always be valid. We can think of an argument as a sequence of sentences with written premises and conclusions, and the premises following logically from the conclusions. That's how we can understand arguments, as we've already suggested. So let's have a look at what inference rules look like. And we're going to begin by looking at modus ponens, which is a very a common way in which we can derive a valid argument. We've actually already seen a modus ponens inference rule. So a modus ponens argument looks a bit like this. Premise 1, if A then B. Premise 2, A. Conclusion, therefore B. This is modus ponens. This is what it looks like. This is the structure of this argument. And really, this form of argument relies on that modus ponens. We can label each part of the argument in their logical terms, and this is really the formula, should we say. We could talk about it like a formula, like in maths. This is the formula for a modus ponens argument. So the phrase if A then B, this is what we call a conditional. Okay, so the truth value of B is reliant on whether or not A is true. So if A is true, then B has to be true. A good way of looking at an invalid conditional, something that is impossible for a conditional to be the case, is if that A is true and B is false. If they have a situation where A is true and B is false, then that is invalid. That is breaking the rule of a conditional. In this case, A, this side of the conditional equation, is called the antecedent of the conditional. The antecedent, the thing that comes first. And then on the other side of the equation, B is called the consequent of the conditional. It is what happens as a consequence of A being true. So there's a direct link between these two entities in a conditional. So we can write a modus ponens argument, the way modus ponens looks, a little bit like this. We have the first being the conditional, whatever the conditional is. If it is raining, then I'll take an umbrella. If interest rates go up, house prices will go down. All these different things. And then the second premise is going to suggest or tell us that the antecedent to the conditional is true. Okay, so if it is raining, then I should take an umbrella. Premise 2 is it is raining. The antecedent is true. A is true. And then we can therefore, if we know that A is true and we have got the conditional, we also know that the conditional is true, then therefore we can conclude validly without any kind of hesitation that B has to be true. By contrast, we also have what are called modus tollens inferences, and you can probably work out just from the way the language of both of these different arguments that this one is tangentially related to the previous one. This inference rule is closely related to the previous one. It's also closely related to the idea of a conditional, again, the if A then B. So we already know that if A then B, and if A is true, then B must be true. So this is really how we define a conditional. But how could we try to find an argument to show that B is not true? Okay, we're trying to work out if one of them is not true. We could try this. Does this work? If A then B, A, therefore not B. No, this is an invalid argument. As we've already mentioned, if A is true, okay, and in this argument A is true because we have written it here, A is true in premise 2, and if A then B, okay, well we've done that here in premise 1 with if A then B, then it would be impossible for B to be false. So this is not a valid argument, this is invalid. Instead what we do is use the modus tollens rule, which looks a bit like this. If A then B, not B, therefore not A. Okay, so what we are doing is, if we can show if A then B, okay, we don't necessarily have to start by proving A first. Okay, we can show that if A then B, we know that if A then sorry, let's put it in an example from the real world. If it is raining, I should take an umbrella. Okay. Premise 2, I should not take an umbrella. Conclusion, therefore it is not raining. It's sort of like mixing the argument up and trying to conclude the argument from a different angle. So if it is raining, then I should take an umbrella. Okay. Premise 2, I should not take an umbrella, therefore it can't be raining. That's a very interesting way of writing it. It shows us the relationship between the antecedent, as we already know that's the first bit, which is A, and the consequent, which we know is the second bit, B, in a conditional. If A leads to B, and we know that B is false, then we can conclude that A has to be false in order for this to be valid. And this is what modus tollens means. The final form of inference is known as reductio ad absurdum. Now, reductio ad absurdum is a little bit more complicated, but at the same time, I think, personally, it's a little bit more easy to understand. So, it's incredibly useful as well to show us that the premises of an argument leads to a conclusion, regardless of the argument. Okay, we could have the most complicated 30 premises and a conclusion, and we could show that it is valid by reductio ad absurdum. Okay, so if we wanted to prove something was true, let's say we wanted to prove that A was true, whatever A is, what we could do is show that the opposite of A is impossible, or it is false. So if I wanted to show that the phrase "it is raining" is true, one way I could do it is I could show that it is not raining, the phrase "it is not raining" is false. If it's not raining is false, then the phrase "it is raining" is true. It has to be true, because only one of them, if one of them is true, then the other one has to be false, and vice versa. So we can prove one to be false, then we can prove by inverse, by reducing to absurdity, which is what reductio ad absurdum means, we can prove that the first one is true. So let's have a look at what this means. Let's see this. Let's see how this inference works. So to prove A using reductio ad absurdum, what we do first is we assume A is false. Okay, we will say A is false. Okay, we should then, what we do, show that by assuming that A is false, this causes a contradiction within the argument, and then conclude that A has to be true. If we were to do this through the formal premises and conclusions, it would look a little bit, it would sound a little bit like this. Ready? Okay, so let's take a traditional modus ponens argument that we've already looked at earlier on, and we say if A then B, A therefore B. That's what the argument looks like. If we wanted to prove it through reductio ad absurdum, okay, we could do this. So instead of saying if A then B, A then B, we would say if A then B, A therefore not B. We would make the conclusion the opposite of what it is. We would what we call negate the conclusion. And we already know this isn't true, okay, because the conclusion doesn't follow logically from the premises. Okay, so if we know that by saying not B instead of writing B, if we know that that is false, invalid, and a contradiction, we can then conclude that B has to be true. Does that make sense? Let's have a look at let me just read it out again, but through the lens of an actual example. So, if it is raining, then I should take an umbrella. Premise 2. It is raining. Conclusion, I should not take an umbrella. Don't forget, we're negating this. We're saying that it's not the case. I should not take an umbrella. Okay, and let's take that example, take that argument. We know that that is false. It is invalid. Okay, it is a contradiction. The premises do not follow from the conclusion. So therefore, we can assume, we've assumed that, and we can show that that is false and invalid. We can conclude that the original argument, if it is raining I should take an umbrella, it is raining therefore I should take an umbrella, is true. That is how reductio ad absurdum works. In a separate course, what we're going to do is look at propositional logic in a lot more detail. Okay, and what we will do is we will do reductio ad absurdum, but on a much larger scale, where we take different logical sentences, and then what we will do is negate those sentences, and then we will graph out the argument into its component parts to show that the negation is false, and so therefore the original argument has to be true. In the next lesson, what we're going to do is carry on with the idea of false statements, and by looking at fallacies. We're going to finish the end of the course by looking at both informal fallacies as well as formal fallacies.